Say, all right, got to put all this together for Friday. But a couple areas that keep cropping up frequently on the email questions. So I want to just take a brief moment to maybe re-emphasize a little bit. Questions about that frontal lobe, the prefrontal area, and then 9 and 40. Whoops, we just lost. There we go, we're back in. But the prefrontal area of 10 and 12, and then moving into more of the association area, that frontal lobe, 9, 46, and 47. So there are a couple I just want to kind of clarify there. And also, a lot of people are asking about akinetic mutism a little bit as far as some fine-tuning with that one. So I just want to take 2 seconds to clarify those. Also on my laundry list, the exam, there's 75 questions, so those of you that are planning your coffee break at 9:15, the exam officially should be done this Wednesday, or this Friday. So anyways, what I wanted to point out, though, is a lot of questions. When you look at this prefrontal area, way up front is your classic prefrontal social behavior, that motivation, and the personality of it all. But everybody's asking about this motor inhibition and planning. And the truth is, if you look at it, essentially, look globally at this. Everything's landing in this prefrontal area and a little bit of Broca's area. So all of this is, bless you, information processing. It's all eventually getting up to here, primary motor, for whatever you're going to do, whatever the moment in time is, whatever your emotional state is, whatever your personality state is, your environmental is, whatever the case is, eventually it's all telling this premotor and motor area what to do. So if you think of the 9, the 46, 44 here is kind of the classic association area for this frontal lobe. It's taken a little bit of everything. And that everything includes the more specific personality piece of motivation, behavior. That should make a little more sense. And if you think about it, the motor inhibition, this is the part that everybody's asking about. The nuts and bolts of motor inhibition is occurring in this, final association area before it throws it up to the premotor and motor area. But your social response, your personality, is initiating the motor inhibition, and that's where those comments are coming from. But that's what a lot of people have kind of, trying to figure out which side of the fence. And the truth is, it's kind of a little bit of an overlap as far as, the net result of both areas is going to, put a social inhibition on what you're doing, and you're not just having these raw, reactions to whatever the moment might be. So it's kind of again, this is all, frontal lobe maturity is, if you think about it, is what's going on here. So that was the one frequent question I've had. The other with the akinetic mutinism, it keeps popping up in all these different points along the way, the vascular slides, the frontal lobe slides, and if I can find it here, what I'd like to just simply point out is don't attach it to a single, 10 through 12 Brodmann's area. Think of it as a bilateral frontal lobe major problem. In other words, classically it's referred to, if the ACA is damaged, it's a bilateral, it's a tumor that kind of expanded and blew out both the right and left side, or the communicating arteries, something like that. So it's involving a lot of the frontal lobe. I didn't get into it too much, but involves the limbic lobe, the cingulate gyrus here that we didn't really, wander into. But the take-home message is understand obviously what it is, but don't attach just a single Brodmann's area of 10 through 12 to it, even though, I probably put it in this discussion, as these areas pop up. So I don't know if that's helpful, helps clarify, but those were some of the email questions I've been getting, and they start coming in multiple times. That certainly warrants a little clarification, I guess. All righty. Any questions, concerns, other than the obvious? What are the answers as far as your exam goes?
I have a couple of questions in Whisper.
Okay. Let me just kind of. Yep.
I know, really far away. So I just want to know how important is like the precentral gyrus and that stuff to our studying, or would you
Oh, the very beginning there's some basic neuro terminology, and you should just know what they are. In other words, I'm not going to ask you a specific gyrus, but you should understand what a sulci is, a gyrus is, what a commissure is, what dissociation fibers are. So, that little beginning of that handout, I think it's got the thing and a quick definition to it, and that's the extent of it. But we're not chasing, in neuroscience, each little lump and bump is named. We're not going there. I don't think I could go there, and I don't think anybody really wants to go there. So, does that answer the question?
Yes, it did. And then my other question would be, we're not responsible for knowing which areas of the thalamus project to which areas of the
A good question, too. Again, as I think I mentioned in lecture, that I've given you more than you need in those slides. They were cut and pasted from a neuroanatomy course I teach where you've got the time to sit there and painfully go for what's projecting. The extent of the thalamus is literally understand who's going through it, but you do not have to memorize who's going from VPL, VPM, the VL, the VA, those individual subsections. With the exception of, there's one little section there that talks about the functional piece of things. In other words, relay nuclei, association nuclei, and some of the deeper, more diffuse nuclei, the intralaminar, and that are involved in some of the reticular and diffuse pain pathways. So that was the extent of connecting the dots of, breaking up this thalamus. But so you'll see about 10 slides with individual nuclei showing there, and you do not have to chase it. And on the outline where it shows you, the hierarchy of those individual nuclei, I won't be asking, the VPM, VPL are part of, what region of the thalamus. Does that answer the question?
Yes.
Okay.
Thank you so much.
Any other questions?
Question, Worcester.
Yep.
In the two pathways of the basal ganglia, the direct and indirect,
Yes.
there's a line under the direct pathway that says cortex to striatum to GP-SNR. Did we talk about that? I missed it. What's the SNR?
Let me pull up the slide just to double check or to confirm what you're saying. I mean, essentially with the basal ganglia, understand, the end result, direct versus indirect, as far as what they do with the limbic drive. As far as the subtle individual pathways like the globus pallidus internus, externus, putamen, all those interconnections, I will not chase you on those individual connections or subthalamic nuclei. And so the ultimate is the globus internus, that last little bit of triangle on the medial part of that basal ganglia, is the last one to talk to the thalamus, and it's always inhibiting the thalamus. The direct and indirect pathways are either encouraging the inhibition or discouraging the inhibition. So that's kind of without seeing what slide you're referring to, the response. But what module was that module?
3.
3. You guys got these memorized. All right. Was it this one you were referring to?
Yeah, I think it's a couple of slides down.
Okay.
No.
Oh,
Too far,
backwards.
Too far. In our notes, it just says GP-SNR, thalamus cortex. I didn't know what the GP-SNR was. I know the globus pallidus, but what's SNR?
Oh, SNR, subthalamic nuclei, there's a compact portion, and I think it's a reticular portion. So again, no, we didn't. I'm not chasing these individual sections. Is that what you're referring to?
Yes, thank you.
Yeah. You do not, as I said, ultimately, this is kind of functionally where I left it off. The substantia nigra, not subthalamic nuclei. Substantia nigra has two little subsections. One's a compacta, another's a reticular, something like that. And that's what the little C is referring to and the R is referring to. But again, that's way too much information. If anybody doesn't mind, we'll just push that aside. All good with that? Okay, I don't see any objections. All right. So as I said, ultimately, just kind of understand the direct pathway, what it's doing to this inhibition on the thalamus, and what the net result is, you know, with its role. Alrighty, any other questions? Chirp, 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 all a good sign? Okay, we'll put those to rest. I guess, where are we? We're on cerebellum, that's where we are. So how many people woke up this morning and said, let's wander through the cerebellum, I just need to know? Don't think many. But it is our tour of duty as we finish off this module. I do want to clarify for the exam on Friday, this section here and forward will not be on the exam Friday. This section 1 with all the clinical discussion of the cerebellum will. So I just want to make sure I've clarified that. So section 2, anatomy function, will save its role until the final exam. And if I remember right, we did wander through some of this. Does anybody have I think we got through a discussion of the deep nuclei all the way downstairs to somewhere in here. Does that sound about right? Essentially, the intention of all this is to just have a good functional understanding of the organization of this cerebellum. And again, we'll be looking at the individual regions of this thing, but I'd like you to just understand that there's multiple, and you'll get to recognize the different kind of clumps, for lack of a better word, of who's coming in to talk to the cerebellum. When it goes in, that information is going straight to a cortex, a region of the cortex. And each region, just like your cerebral cortex, has a certain role, for lack of a better word. After it gets up and talks to that cortex, and it's landing on those Purkinje fibers in the cortex, it's now coming down and landing on some specific deep nuclei of the cerebellum. Each one of these deep nuclei are associated with a different region of the cerebellum. Then after that, they get pushed out through the certain peduncles that we'll talk about, mostly the top one, some on the bottom one, none on the middle one, and go do their thing, whether they're heading back up to the thalamus and the cortex, or they're heading downstairs to the spinal cord. So that was the intention of this anatomy and function piece. We're going over the quote-unquote schematic. So that's the approach I would take to that region of these. So did I go through the individual deep? Well, actually, is this where we landed off? Is this, or did I even not get this far? I didn't get this far? Okay, so I'll back up the truck here. So I think our discussion landed. We talked about the inputs. We talked about two types of fibers, climbing fibers, mossy fibers. And I think we had briefly talked about that they eventually land in these Purkinje cells. I joked about alcohol likes to find those cells. That's one of the reasons of, you have all those cerebellar signs, after you've had a few beers. So that's, I think, where we had finished things off. And then the discussion of these deep cerebellar nuclei that I had just referred to. So as things have been up in the cortex, they're now being pushed back down to specific deep nuclei that eventually, in turn, will take that information and send it back into the CNS. So that's a pretty simplistic description of it. There's three types of these deep nuclei, the vestigial, interpost, which is really two separate ones within there, and then this dentate ligament. You can tell my brain is fine. Dentate nuclei. But we will revisit these at the end of this thing and talk specifically about where each one points. So just take the concept that each one points to a specific functional area. Each one kind of has a functional role. All right. Again, I think the slides just kind of give you picture after picture. This picture is probably valuable in the sense we're about to look at it, but this cortex that I keep referring to having a specific function, is divided up into regions that we'll talk about. And it's each one of these regions that talk to a specific deep nuclei. So this lateral region here talks specifically to these guys. This paravermis and vermis region will talk to these guys and a little bit of these guys. So again, they have very specific connections, if you will, between the cortex and each one of these. All right, so we'll look at these subdivisions that I just chatted about. And as I said, the sad part of the cerebellum is anatomy-wise, it has its own things you point to and say there's the anterior lobe, posterior lobe, but they're not necessarily functional divisions. So often there's two ways of looking at this thing, quote unquote, functionally. One is this longitudinal description that we'll go over, and then two is the phylogenetic or evolution of the cerebellum has a functional division way too as well. And so there's just a little bit of limitation of this longitudinal one that we'll be going over in a moment. But I put these two slides at the start of this, and whether you know it or not at this point, it's a nice synopsis of sort of what you need to know. Next, or Module 6, probably next week we'll get to it, we'll be going over the tracts of the spine. And so this will make a little more sense once you've done that. So if this part looks a little bit, kind of just put it on the shelf or in the parking lot until we get there. Today we'll be looking at the individual regions and what they actually do in terms of motor output, motor learning, and blah, 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 those kinds of things. So that's what this slide does. This next slide is a nice shortcut to show you what I was talking about with the individual regions talking to a specific nuclei. So the lateral hemisphere connect directly to the dentate. Those dentate project to a specific spot, back up to the motor cortex actually, and have a certain function. Meanwhile, this is known as the paravermis. Actually, it speaks to these interposed, which is actually a collection of two nuclei, and then this one, which is the very middle region, we'll take a look at it, talks to this vestigial nuclei. Then last but not least is this thing called the floccular nodular lobe, which doesn't really use a deep nuclei. It just goes in and out of that cerebellum with the cranial nerve 8 to do its thing. So that's what we'll be going over for these next few slides. And as I said, we'll look at it longitudinal first, phylogenetic second. Some of it's overlap, but some of it has its own distinct division, if you will. So when you look at this thing, where this comes from, you'll see this schematic all the time. But essentially, if you take the 3D-ness of this thing and you take it off the back and you kind of peel it out and flatten it out, that's where they come up with this schematic. So that's the orientation, if you will. So this midline that's wrapped around is known as the vermis. Then you move out of midline a little bit, and it's known as the paravermis. Makes sense nomenclature-wise. And then when you get out to these guys, which is a majority of the surface area, is this lateral hemisphere. Meanwhile, up front, these two little odd nodular lobes known as the floccular nodular lobe, which is the oldest part of things, and it's involved with a lot of the core stuff, your visual and neck and type reflexes and core postural type reflexes. So that's how this comes about. But when they look at longitudinal, they look at lateral, paravermis, and vermis, but this thing doesn't fit. It goes straight across, and that's what I mean by the logic of these divisions. So by definition, you should know what the vermis is, paravermis, lateral hemisphere is. Then you should be able to connect the dots to the deep nuclei, so that's the beauty of this slide. It's giving you a nice all in one lump sum, everything we've chatted about so far. So the vermis, which is almost the oldest area, talks to the vestigial, the paravermis talks to the interposed, and this lateral talks to the dentate. And we'll get to where they're going in a little bit further down the line. Meanwhile, the floccular nodular lobe, that funky, odd, thing deep and in the front of this cerebellum, just interacts directly with the brainstem, the vestibular nuclei, cranial nerve 8 sitting right there in the pons of medulla, talks directly. There's no deep cerebellar nuclei, if you will. This is a little generic, but it gives you a little hint as to where you're going as far as function-wise. But in general, if you think the more central and older, the more core motor role, and the further out you go, the more defined learning, high-end kinds of human movements, these skills that we learn to do with motor planning, et cetera, and we'll get to those. Looking at it in a phylogenetic logic system. How are you, Alan? What's up? Sure did. Why? What's up? Yep, it's all good to go. All right, you can teach an old dog new tricks, I guess. Looking at this thing from a phylogenetic genetic standpoint, as I said, the oldest is the vestibulocerebellum, which is essentially the floccular nodular lobe. The spinocerebellum is a combination of that vermis paravermis. And then you get to one more area known as the cerebrocerebellum, which is the lateral region, if you will. It's the newest. It's what makes us uniquely human and able to do all the motor things that we do. So as far as the longitudinal, what you need to do is just kind of know what the anatomy is, essentially visually. It's these the midline of the thing, so that's pretty straightforward. And have a understanding of its functional role. And so I've got a pretty big laundry list of things down here. But what I'd like you to think about is essentially think postural control. In other words, for you to do all these fine-tuned high, skills, you need a central foundation. You need a postural core stability, if you will, for lack of a better word. And this vermis is the very basis for that. So as you dance around all this, there's lots of discussion here, but that's kind of the core foundation, if you will, to allow all the higher end motor skills to go on. But also involved in some of the deeper postural reflexes, things you don't think about, whether it's anti-gravity or whether it's some of the visual type of things that go on. Again, when you move your head, there's a lot of complex or coordinated activity going on to coordinate your visual input with your physicalness of moving around and looking around and reacting and doing. So that's, in summary, the paravermis, the vermis. The paravermis, the next one, starts to move out a little bit. A, by location, that's easy enough, but by function, too. It's starting to hold this theme of proximal still, but now we're moving out to extremities where, again, where all this complex movement, highly human skill things come into play. But this is really the foundation and the basis for those extremities. So when you look at this thing, it goes distal limb coordination. And essentially what it's doing is using the postural control from the vermis, now taking real-time information about, hey, I want to pick up this paper clip, and if I'm going way over here, I'm missing it. There's sensory input telling me, whoops, I shot too far, I shot too short, and it's real time. It's as I go telling me I'm missing my target and correcting for it. So it's plays a major role as far as that coordinated distal limb activity, if you will, to make things, your synergy of movement, if you will. So when you look at all this, that's essentially what it's quote-unquote saying. When you look down here, it says respond to proprioceptive sensory input from blah, blah, blah. And basically what it's saying is as you move, again, you don't think about it, but all the mechanoreceptors in your arm are doing something. Muscles are lengthening, joints are moving, and all that feedback is telling you it's what your brain wanted to do, but it's doing it real time to make sure, even though your brain's saying pick up the paperclip, making sure the hand is going to pick up the paperclip. And so it's real-time feedback for that to occur, if you will. So that's the paravermis. And then last but not least, and so I should back up, So often these are kind of lumped in this motor execution, if you will, but I kind of like the idea of that core stability foundation piece of it as opposed to just being able to do something. You need both a little bit. You need the feedback, but the core foundation for it all to occur. And then finally, the lateral zone, pretty straightforward to where it is. Netter painted it nice and green, pretty easy. But function-wise, this area is the complexity. This is the area that's involved in learning that skilled movement, planning that skilled movement. It's kind of like the subconscious pre-motor area in a sense. So when you go to learn whether it's an athletic skill, a backhand, whatever the case is, you're using a lot of this cerebellum to set pathways down so you don't need to be putting it up in the area 6 and 4 and consciously, wasting synapse time. And by the time you're up here, the ball's already by you. You need to kind of get those connections, make them happen, make them work. So this area is pretty critical in all that motor learning, if you will. So that's where this discussion of skilled coordination, skilled movement, planning, those kinds of terms describe this area. When you look at cognitive emotional learning, really that's connecting the dots with the tripod of the whole physical skill. There's the physicalness, but there's the emotional piece of it, and the cognitive reasoning as to the why. So again, it's a little bit multimodal, if you will. So it has a pretty big influence in that regards. So the cerebellum, way back when, knee-jerk reaction, coordination, everybody says that, but this is where that whole learning piece comes into. People don't think of the cerebellum as involved in learning activity. So those are the three zones. If you look at them from a longitudinal, the only problem is it doesn't discuss too much about this vestibulocerebellum or this floccular nodular lobe. So now what we're going to do is look at this thing by development or, again, phylogenetic divisions. And again, it'll sound like double speak, so we can go through most of it pretty quickly. So starting out of the gates, each of the regions, the oldest, next oldest, and newest. This is sometimes neocerebellum or pontine or pontocerebellum. So the first one, the oldest, vestibulocerebellum, you should be thinking this blue knee-jerk reaction of floccular nodular lobe. It often includes a little bit of this deep inner vermis, if you will, and that's where when you start putting this together, you're going to see this little bit of overlap between floccular nodular or vestibular cerebellum and vermis function. You're like, wait a minute, isn't vermis a little further out, a little away from? And that's the reasoning why. So anyways, that's the vestibular cerebellum. A, know it's the oldest part. B, know essentially what the anatomy of it is. As far as connections, you should have a few basic understandings of each of these regions. Vestibulocerebellum, it's nice and easy. The name tells you what's going on. Basically, the input coming to it is all of the vestibular input from cranial nerve 8 directly or from the vestibular nuclei in the brainstem. So obviously, vestibular input, nice and easy. It goes up into the cortex, and now it's going to come back down. And the only difference is it doesn't have any deep cerebellar nuclei that we had chatted about before. It doesn't make a stop there. It just shoots right back out and goes to wherever it's going to go, whether it's back to vestibular, to reticular, to some other pathways, if you will. So that's a simplistic discussion of what the take-home message should be here as far as how it goes in, how it goes out. And eventually we'll be talking about which column it goes out, whether it's superior, middle, and inferior. But I've plunked it here. Primarily, the oldest stuff is going in and out of that bottom peduncle, which will lead to future slides here in a moment. This slide here, it's the exact same thing. If you get a moment, if you like to see the entertainment factor, again, these guys put together a pretty decent, very nice overview of the neuroanatomy and functional ways. So if you cut and paste the link, you'll be able to see some interactive versions of each of these regions, that's all. Okay, so function-wise, what's it do? I'll sneak down to this first. Plays a huge role in that core stuff. Remember we said the eyes and where you're orienting that horizon and what you're doing, whether it's reactive, whether it's any of those visual reflexes. Again, you don't think about it. It's old, just core, innate, functioning type role as far as visual core, motor control. But the other piece is that deep postural stuff, as we said earlier. Think of central to out, and you have to have your central in the right place. Doesn't matter what your eyes are doing or your hands doing. If your neck and your posture and trunk aren't in the right position, you're still not going to be able to accomplish task at hand. So it has a very deep core role in maintaining and keeping, that neck in the right place, turning the head in the right place, and encouraging the trunk eventually to go in the right place, although that starts to sneak into the next layer out, which is the spinocerebellum and the vermis. So muscle tone, if you look at that all by its lonesome, and what does that mean? But muscle tone is all about postural control. You have a certain amount of muscle tone to keep your head upright, to sit in a chair. So that's all it's referring to. So that's the oldest part, vestibulocerebellum. The vestibulo-ocular reflex, in theory, for you to turn your head, your eyes should adjust and stay focused on whatever they need to do. And then there's different subsets of what you can do with that, if you will. Obviously, those of you in front-end EMR or EMT or paramedic settings, and you're establishing or ER settings, with some of the testing techniques, you turn the head and you're just looking at the eyes to see if they're responding appropriately. You're testing your VOR patterns. So in general, you turn your head one way and the eyes should be able to stay focused on what they're trying to do. However, there's other terminology to either kind of suppress or overcome that. In other words, if I purposely want to turn my head and look this way, I've got a quick saccade or quick motion of my eyes to focus that way, and I'm suppressing that VOR a little bit. Or if I really wanted to, I could take a piece of paper and say, all right, I'm turning my head to left, but I'm staring at the paper the whole way, and I'm purposely, consciously suppressing some of those VOR connections or pathways. So that's an example of the vestibulocerebellum and kind of coordinating what goes on with your neck and core function that way. Meanwhile, moving up the chain, spinocerebellum. This is nothing more than a combination of the vermis and paravermis. So that's really a simplistic way to look at this thing. So the discussion really is kind of combining the two. So that's all we're really talking about. So essentially, information coming in, as we said with the paravermis, was that, mechanoreceptors and kind of telling you real time. That's through the spinocerebellar pathways. We haven't done them, so it's kind of the cart before the horse, or whatever the saying goes, that we'll get to. So some of this might not, make intuitive sense until we've kind of run the gamut of finishing off the brainstem and the spinal cord. But the real thing I'd like you to do is connect the dots to who's talking to who. Again, the paravermis is talking to these interposed nuclei, which is a combination of two. And then the vermis is talking to the fastigial nuclei. That's a very simplistic way to divide it up, but sometimes there's a little gray area when it comes to this fastigial nuclei. So ultimately, when you look down here, you go vermis, where's it project to? Paravermis, where is it projecting to? And again, we haven't gotten into all of this, but I'll put it in simplistic terms. Vermis core trunk stability. We're going to do the spinal cord tracts, and there's a lot of tracts that start out reticulospinal, vestibulospinal tracts. These guys are these deep core things that keep everything about your trunk in line, for lack of a better word, keeping the muscle tone in line. So it makes sense that the older, as we said, its role was this core trunk control. Paravermis, when you see where that projects out to, again, we said its role is a little bit more with coordinating this distal limb activity, if you will. It's kind of making sure the proximal part of this fine-tuned thing is doing what it should. And it's got down here red nucleus. And again, when we get to the spinal cord, these guys all run down together in the front of the cord. This guy runs down on the outside, or the lateral part of the spinal cord. So two separate regions, two separate functions, if you will. And the lateral part of that spinal cord is involved with all the distal extremity activities. The anterior and the medial part of that spinal cord is your core trunk stuff. So, eventually when we get there, this will be even more, intuitive to think of this, but that's the basis of where it comes from, if you will. But the nice thing is, if you're looking at the spinocerebellum as a whole, it's really just a combination of those two things. So you're talking about all one thing in a category. Function-wise, all I've done is just cut and paste literally the function of the vermis and paravermis. So there isn't too much more to add to either one of those other than you're just putting in this classification system, lumping them together. This is a little simplistic. The problem with the cerebellum, up here for the test, you're memorizing Brodmann's area, 44, 45, whatever it gets blown out, you're measuring, you're trying to localize the area and connect it to a function or a loss of function. The cerebellum is a little more difficult to do. It's not that clean, for lack of better words. In other words, you can't localize the lesion in there and really have this nice, clean, predictable functional loss. But with that said, there is kind of an attempt to do that, and that's what these slides, when we put, lesion may produce, it's just kind of a general localizing approach to it, but it's not, there's definitely a little bit of overlap, if you will. So again, since these things are very core, postural, muscle tone, all of this should make sense as to the hows and whys. Ataxia, the difficulty in being able to do that coordinated movement really stems from the core, clumsiness of not having the stability to do it. In other words, you're doing it, but you don't have the core piece of things to execute it. So that's a little discussion trying to connect the dots to the functional piece, but not quite as clean as the cerebral cortex. All right, last but not least, pretty easy, is the lateral hemisphere or the cerebrocerebellum, neocerebellum, referring to new. Somewhere I've got Patho or pontine cerebellum, which is really describing who's connecting to it. But basically, it's the lateral hemispheres. And when you look at the connections of these things, ask, okay, who's talking to it? And essentially, it's all the input coming upstairs from the motor cortex comes down, bless you, and it lands in these nuclei known as pontine nuclei, if you will. So you've got a chunk of the motor cortex that goes down this track, lands in the pontine nuclei. They, in turn, throw it into the cerebellum and throw it into these lateral hemispheres. So that's where the name pontine or Patho cerebellum comes from. It's just describing the pathway to get there. The caveat is this motor cortex stuff comes down, lands in the pons, and it throws it through that middle cerebellum. That's the only, peduncle. That's the only thing that middle peduncle does, and throws it into the lateral zone. After that, throws it down to the dentate nuclei, and then it's going to push it back up to the motor cortex. So basically, this new stuff is nothing more than a circuit of the motor cortex coming downstairs, talking to the cerebellum, getting fine-tuned a little bit more, and getting thrown back upstairs to the motor cortex, and then your final output, if you will. So that's kind of a functional overview of each. So if you look at it, again, this is nothing more than cut and pasted, but clinically, if you've lost some of these things, this is where that laundry list of dysdiadochokinesia and all these other dysmetria, intention tremor, dysarthria, all these synergies or dyssynergies that show up are because you're not able to, create this computer program of real-time planning to execute that fine movement. So again, if I'm trying to hit this paperclip, that I've lost the ability to really fine-tune that and plan it, and I'm overshooting, I'm undershooting, and missing it, finger to nose, bang, bang, that kind of thing. Intention tremor, close, but compensate, shaking, the closer you get to it. So those are the synergies that we're talking about. So that's a little overview of the functional divisions. But appreciate some places are going to talk about longitudinal divisions. Some are going to talk about these phylogenetic divisions. And that's just where they're coming from. All right. Section 4 is nothing more than talking about the connections, superior, middle peduncles, and inferior peduncles. And the only thing, these are nothing more than conduits. We just need to look at them as individual functional pieces of this thing and just define who's going through it. That'll help reinforce what we had chatted about before. So these peduncles, again, is nothing more than a bundle of these white matter, by definition, going in and out of the cerebellum. So the top one connects essentially to the midbrain, a little bit of the pons, but mostly midbrain as far as its location. Sits right there. But function-wise, essentially, everybody's going out of the top one. So if you think of the top one, a majority of information through that conduit is all exiting this cerebellum. But the only caveat is there's a little discussion or debate within the neuroscience world, and there's a lot of discussion that, there still is input. Some of this spinocerebellar stuff is coming in. And again, we haven't got there, but that's where I'm quote-unquote putting the little asterisk, if you will. But for our purposes, essentially, no afferent is passing into the cerebellum. When you look at this thing, this is a fairly simplistic schematic, but not too bad. Superior, middle, and inferior. And essentially what it's showing are all the deep nuclei exiting out. And that's what I did not put in your outline, so I put this as a handy-dandy reminder to myself to point that out. The reason it's not there is some discussion about some of these guys going out that direction. So that's why, if the neuroscientists can't make up their minds, I don't think we need to, be as black and white as well. So that's where it's coming from. Everybody's going out and going to do whatever they're supposed to do. So lateral stuff, vermis, paravermis, deep cerebellar nuclei, all exiting out of the top one. So pretty straightforward. Middle one, this one's real easy. The only thing is that pontocerebellum pathway. So all that stuff from the motor cortex coming downstairs, landing in these pontine nuclei, they go in. Where are they going to? Lateral hemisphere. End of story for the middle peduncle. So it's just the front end loop of that lateral hemisphere loop that talks to the motor cortex, which is the cortex, talks to sensory cortex too. I think that's what this slide is just reinforcing. Lastly, the inferior peduncle. This is where that gray area is. There's kind of some loose discussion about or inconsistencies, if you will. But the bottom line is, when you think of this bottom inferior peduncle, think of the vestibular pathways we discussed in the old stuff, the flocculonodular stuff, the cranial nerve 8. Basically, it's going in and coming out of this conduit in this inferior peduncle. There is discussion that the other stuff that's going to go into the vermis, paravermis, the spinocerebellum stuff does come in through here. So that's where you see the confusion is some people say some of that does up top, some does it below. I will not ask you a question splitting the hair between those two. If they can't decide, we're not going to worry about it, that specifically. But you should understand these guys, the old vestibular stuff that's going through there. So what this schematic does not show is the vestibular nuclei, the information exiting out, going back to the vestibular nuclei and doing some of the core things we had chatted about. So there's a couple of bundles, if you will, within this inferior peduncle, restiform and juxtarestiform. It makes sense simply by it. I'll speak about this one first, and I'd like you to just connect the dots. When I talked about the vestibular stuff going in and out, basically connect the dots that it's a juxtarestiform body where that happens. And then, the restiform, the other white matter, is simply that whole discussion of this spinocerebellar stuff coming in to the cerebellum that way. But there's discussion that it also goes up and over and into the top, too. So that's where the breakdown of these two little subsets are coming from. So this one, star this for definitely that's a black and white answer. This is a little more, debatable in the neuroscience world out there. Okay, and then this is just a nice slide showing you the differences between the two. The dark stuff is the spinocerebellar stuff. Remember I made the comments. The mechanoreceptors of your arm, your joints, everything's coming up, eventually talking to that paravermis area, and that's the spinocerebellar pathway that it gets to. So that's that information, theoretically, that's coming in, going to that paravermis and making all that real-time connection. And this stuff is just in and out pathway of the vestibular stuff. So those are the peduncles. Last but not least, I know we'll kind of cram it in and then put the cerebellum to rest. This is just looking at the same thing we already chatted about. So really the only moral of the story is know each deep cerebellar nuclei and know functionally who's talking to it and have a rough idea where it's pointing to, because that we haven't hit quite as hard in terms of detail. So the vestigial are up first, which is the core stuff. So again, floccular nodular lobe doesn't have any deep cerebellar nuclei. Vermis, oldest stuff, that goes to the vestigial. When you look at this lineup here, it really is just arranged in the same order. The vestigial is the most medial, midline ones. You move out a little bit, just like the paravermis, and you get to the interposed of the emboliform and globose. And then you move out to the lateral, which is the dentate nucleus, and the biggest two, the most surface area. So their arrangement mimics where they had talked to in the cortex of the cerebellum. So the vestigial, as we said, most midline, and essentially it's going to take the information from that vermis, take that core stuff, and throw it out through the superior cerebellar peduncle like we kind of looked at in that top slide, although there's some little discussion. Most people are on board with this. But the real key is it connects with vestibular nuclei and reticular formation. And if the take-home message, the cart before the horse, those spinal cord pathways are deep core pathways to keep your trunk upright, keep it doing what it needs to, muscle tone, and reflexes, anti-gravity, all that kind of stuff going on. So that's the vestigial nuclei. Sneak forward to the interpose. We moved out. It's really just a pair of them on each side, this globose and emboliform nuclei. And this is really connecting to that paravermis region. So when you look at it, as far as function, it's the exact same thing, that coordination of that distal limb movement that we had chatted about. Compares intended movement with actual movement. That's that, feed-forward feedback that we had talked about. Real-time feedback to make sure your hand lands in the right place to pick up the coffee mug. And then last but not least, the dentate lateral zone. We've already beat this one to a pulp, I think. So the lateral is coming down, talking to it, and it's now sending the information back out up to the thalamus. So it's going to go to specifically your motor cortex and also your 3-1-2 cortex as well. But again, it's the whole motor learning piece of the same thing as lateral hemisphere, if you will. So as I said, it's really talking about the same thing 42 times over, but it's kind of anatomically looking at each part of that cerebellum through it. Last but not least, as I said, I made comments before that floccular nodule lobe doesn't have any deep cerebellar nuclei, although sometimes functionally they refer to the vestibular nuclei that way, but they sit in the brainstem. All right, we'll put that to a rest. So those of you that were dying to know about the cerebellum this morning, your prayers have been answered. Those of you that weren't, your prayers were answered too, because we're taking a break. So why don't we take 5:10 and we'll regroup for the brainstem. Yep, question? Are you serious? Module 4.
5, not up.
Oh, boy. Okay, I will, is this module 4? And module 5's not up? No. Oh, boy.
Correct.
I will rapidly do that, and we can rapidly try to print it out, or if you guys have your iPads up in real time, I will take that into account as we go through it. I'll try to help process that. My apologies. It's yes, it's summer term if you haven't noticed. Thank you. All right, we'll regroup whenever I get this done.